So, shall we start? Hi, everybody. Yeah. So, sorry for my bad voice. I don't know. I hope that it's going to get better today, but apparently it's getting worse. So, the bad thing is that you need to hear it for 2 hours. Yeah. But no other choice. So, we ended up talking about optimizers last time. So I just use this microphone more efficiently today, so you would hear me better. Let me make sure. Yes. So you can hear me better now, I guess. Yeah. Okay, so we ended up talking about optimizer last time, and in that one we talked about the fact that if we use vanilla stochastic gradient descent, then we're going to have some troubles, right? And the troubles are coming mainly from the variance we have in our estimator, right? So if you remember when we talked last time about the stochastic gradient descent, the issue with the stochastic gradient descent was that it was trying to just save you some time. And if you want to save time, it means that you are averaging your gradient over mini batches instead of batches, right? The whole batch. Mini batch is smaller, so it's going to give you higher variance, right? And if you use that one in the very simple form, the vanilla form, then at the end of the day, you're going to have some troubles. So the question is how we can get out of this trouble. So we had a short discussion on the fact that if you use an optimizer at the end of the day, you're going to have something, we call it convergence rate. And the optimal thing with the convergence rate is, what is the optimal convergence rate? How do you want your optimizer to converge? Linearly, great. So linearly, it means that it's going to drop, the optimality gap, the distance, the difference between the point that you are working on and the optimal point, the minimum point, is going to shrink exponentially with the number of iterations you are doing. And this is a great thing because in a very fast manner, a few iterations, you're going to get very close to your optimal point. But the fact is that in general, we're going to have sublinear case, right? And do you remember that what was the convergence rate? What was the form? Or how does it drop with the number of iterations with vanilla stochastic gradient descent? It was not exponential, definitely. 1 over t, 1 over number of iterations. Great. So if you use a stochastic gradient descent, then you are going to drop 1 over number of iterations. So that was the challenge, and then we are trying to improve as much as we could, and people have done it a lot in the literature. So indeed, the literature on optimizers is is much older than literature on numerical approaches for deep learning, and this makes sense because these algorithms are not only used in deep learning, they're also used in other disciplines as well. Anything when you want to do optimization, at the end of the day, you need an optimization algorithm, and this had been developed in all of those approaches as well. So what we're going to do today, we're going to start with a couple of them. We're going to finish this part today. So we're going to just get into a few key ideas in optimization or designing optimizers so that when you are using it in practice, you do know what you're doing, okay? So let's start with the first one, which is the gradient, learning rate scheduling. So the idea of learning rate scheduling is that, this is the idea of learning rate scheduling. The idea is exactly the one we talked in the first chapter. So when you are doing the optimization, the best thing that you can think of is that if I want to just move fast, I can start by very large learning rate, and then I can gradually reduce it. Because if I am somewhere at the top and I want to just hit the bottom, so I can just skip, a good part of the way by just being very, very fast or taking a very large step. And then once I get closer and closer to the optimum point, then I'm going to just make it smaller and smaller, right? So this is the idea. So the idea in general is that you're not going to use a fixed learning rate, but rather you're just doing any scheduling on it. And the scheduling on it, it means that in each iteration, you're going to decide what is the value of your learning rate, right? And you can do it always, right? But the question is that how you can design it, how you can choose it. So a very basic idea is that you start with a very large guy, so say 1 eta 0, which is a very large value, for instance 0.1 or 0.01, something quite large. And then gradually in each iteration you just drop it with some specific form. So you can, for instance, do it in this form. This is a linear decay, so this is learning rate decay, so you drop it with a number of iteration. You can do it polynomial, so you can just take the number of iterations that you are to a polynomial, to a power p, or you can do it exponential. So these are classic ideas for doing the scheduling, okay? But the point is that if you use these ideas, it's not going to help you a lot. So when you do these ideas, I mean, they are going eventually, if you start with a very big learning rate, it's going to help you to some extent, but it's not going to change the fact that you are just converging very slowly. It's just minorly would help you in that respect. One other idea that people use is more of a practical trick, and this idea is that we do it this way. So we start by training, and we just set our learning rate to something fixed. For instance, 10 to the power minus 2. And you keep on doing the training. When you do the training, if you just track the test accuracy or test loss, you're going to see at some point that this curve is going to show you a plateau, right? We talked about it last time. So when you do it, it's going to just drop, and then it's going to get into a plateau. Once you get into a plateau, maybe you can try to reduce your learning rate once again. Maybe with some constant factor alpha, which is smaller than 1. Okay? So if you do that, then again you keep on training, and maybe again this is going to drop and meet another plateau. And you can keep on doing it till it just converges. So if you want to think about it, for instance, you start with training, your eta is quite large, so you start with that one. You're going to keep doing the training up to the point that you get here. And when you get here, you're seeing some sort of plateau. So you see that your test risk is not changing anymore, meaning that basically you are just getting close to the optimal point, but maybe you are just bouncing around it, right? So now maybe you can get the idea to just reduce it. Maybe you reduce it by some factor. Typical factor is 10. So you drop it with factor 10. You divide it by 10. For instance, if you were using 10 to the power minus 2, now you're going to change it to 10 to the power minus 3, and you keep on training. And you might see again another plateau. And you can keep on doing this till you see no more change. Okay? This is one other idea. This is more practical, but some people still use that idea. Any questions? Everybody's clear? No question? Did you get anything? Because with this voice, I don't know. Okay. Okay, so now the next thing that, one thing that I wanted to mention here, if you're using PyTorch, you basically have access to a scheduler. So you don't really need to implement any of them from scratch. I mean, you can just use this particular library learning rate scheduler, and then this is going to do the job for you. You just need to know how to use it. So it's going to be a good idea to take a look at this one. Okay? So that's it. But if you use learning rate scheduling only, this is not going to help you so much. So you need to just do a better approach, and a better approach that you can use is to just use the idea of momentum. So basically all optimizers that you use nowadays, they all use the idea of momentum. And what is the idea of momentum? The idea is that when you are using gradient descent or a stochastic gradient descent, you have gradient terms, the sample gradients, which are very noisy, right? They're changing from time to time, from one iteration to another. So the best idea that you can come up with is to just reduce this variance. And if you have multiple samples of a noisy thing, one idea to do it is to just compute the moving average, right? So do you know what is the moving average? No? So if you have something like this, one sequence x1, x2 till xn. And what you know is that every single of them, so every xn is basically one true value x plus some noise n. Okay? So there is maybe something else here instead of nz. You have your true value, this is the average value, and this is your noise. Okay? So this guy could change from one sample to another, right? But this one is not changing, correct? Now, what you are doing is that you see x1, then you see x2, then you see x3, and at each time you want to just compute a better approximator for x. So what you can do, you could say that, okay, x2 is x plus z2, right? And x1 is x plus z1. Now if I compute beta times x1 plus 1 minus beta times x2, what it would be? And beta is something between 0 and 1. What it would be? Beta times this guy, it's going to be beta x plus beta z2, right? Sorry, beta x plus beta z1, right? 1 minus beta times this guy is going to be 1 minus beta x plus 1 minus beta z2, right? What's going to be the sum? So what is the first term in terms of x? It's going to be x itself. Beta x plus 1 minus beta x is x, right? So it's x plus beta z1 plus 1 minus beta z2, right? So you still have x, correct? Right? What is this? This is average of some noise, right? If you do averaging on the noise, what's going to happen? The variance is going to drop, right? So at point x2, instead of taking x2 itself, you can compute its moving average, right? You get this guy, you computed the average with this one, but you don't use x1 plus x2 divided by 2. You use some beta. And this beta could be in general very close to 1. Okay? Now, if you got into x3, once you are at x3, you don't really need to do it anymore on x1 and x2. You could get this one. Again, you multiply it by beta, and then sum it up with 1 minus beta x3, right? So you're going to end up doing something like this. At every time t, you're going to have your xt being beta times xt minus 1. This is the moving average you computed last time. And then you add it up with 1 minus, okay? So this is x bar. And this is 1 minus beta xt, right? Now, this guy is your moving average. And each time you compute it, you are still computing an estimator of true x, right? But the only difference is that you are reducing the noise power. You are reducing the variance. You got the idea? Is it clear to you? Right? Any questions? Okay, so this is what we call it moving average. So this is your moving average at time t minus 1. This is your moving average at time t. Basically the average of what you have computed up to this point, and the new sample. So you can do the same thing with your gradient, right? So at every single time, you're computing a mini batch gradient, which is a noisy sample of the true gradient. So maybe you can just replace it with its moving average. And that moving average is what we call it momentum. Everybody's clear? Yeah.
Could you give a concrete example, like a small concrete example?
Yeah, sure. Why not? So, for instance, say x1 is 3, okay? What I'm gonna do, I'm gonna set my x bar 1, my moving average at time 1. This is moving average, writing it here, moving average at time 1. It is going to be exactly the guy itself because I don't have anything, right? And say I set my beta, to 0.9. Now, at the next time, I see x2 equal by 1. Now, what's gonna be my x bar 2? It's gonna be beta times x bar 1 plus x2, or sorry, 1 minus beta x2. Now, this guy is 3, so it's gonna be 0.9 times 3 plus 0.1 times 1, right? So it's gonna be 2.8, correct? Now say you're at time 3, you see x3 equal by 2. Then your x bar 3 is going to be again beta times x bar 2, what you computed in the previous time step, plus 1 minus beta x3, right? So it's gonna be again 0.9 times 2.8, this is what we computed last time, plus 0.1 times 2, right? So this is going to be 1.8 plus 0.72 plus 0.2. So you can do the math. So I'm bad in that. So it's gonna be okay. 2.72. 2.72. Right? And you keep on going. Everybody's clear? So when you do this, you can see it here. 3, 2.8, 2.72. So you see that the variation in this value is changing, right? Whereas your true value is changing a lot. 3, 1, 2, right? So it's jumping up and down. But that guy is not doing that, right? So it's a better estimator. It has low variance. Everybody's clear? Great. So the idea of momentum is basically to replace the gradient with its moving average. So in every time in the stochastic gradient descent, what we do, we just compute the gradient first, and then we update our weight using our gradient. And if you do a scheduling, it means that you are going to schedule your learning rate as well, right? Now, the thing that you do here now instead is to replace that gradient vector with its moving average. You start with the first gradient. Every time you see a new gradient, you compute the moving average using some factor beta. And this beta value is usually something very close to 1. So if you do that, then your update rule is going to look like this. So every time in every iteration you compute the moving average, and then you're going to update your weight, not with the gradient itself, but with its moving average. Everybody's clear? Any questions on that? Okay, so if you got no question on that, then let's go for the Nesterov idea, the Nesterov momentum. So if you use PyTorch, you might have seen this. It is already implemented in the SGD function in PyTorch. And this is one of the most key ideas helping a lot in improving the convergence rate. So this is a bit tricky. It would be great if you look at the board right now. So, use this one. Okay, let's say that I am at the point, everybody, just look at here because it's a bit tricky. So it would be great if you just see the geometry. It's going to help you understanding it. So say I am at the point WT. This is the weight at the iteration T, right? And now I want to update my weight. How do I do it if I'm using momentum? I'm going to get this guy, and then I change it with my learning rate eta times the momentum at time t, right? Correct? So say, for example, this is minus eta mt, then this is the new point. This is going to be the Wt plus 1 if I use the basic momentum approach, right? But can I open up this term? Let me open up this term for you. What is mt? What is the momentum at time t? Can you tell me? Beta mt minus 1 plus 1 minus beta gradient at time t, right? Okay, so what I can say that this mt is basically one guy here, which is mt minus 1 multiplied with minus eta. And I do have another guy, which is gt. And this is multiplied again with minus eta. Correct or not? And of course, I do have the beta value as well. So there is one beta here, and there is one minus beta here. But they are not important, really. Right? So this guy plus this guy is going to give me this vector, and then I move in this direction. Right? But before I see this guy, gt, I do already know that. What is gt? Can you tell me? What is this guy? What is gt? This is the gradient at which point? Wt, right? So this is going to be the gradient at gradient of r hat at point Wt. Now the question that people asked was that, or maybe Nesterov asked actually, was that why should I compute my gt, the gradient, at this point? Because I already can go to this point. Correct? Before I see gt, can I go to that point? Because I have mt minus 1, right? So what is this point? Can you tell me what is this point? I'm gonna call it w hat. What is it? Just tell me, and I write it. W hat, it is Wt, great, minus, say it, eta, then beta mt minus 1, right? This is w hat, right? So Nesterov said, why should I compute gradient at this point? Maybe I can compute g hat, which is at the point w hat. And then instead of computing the gradient directly here, I get another gradient here, which is g hat t. This might take me to a better point. So this was his idea, and it's not simply an intuitive idea, it has a proof that you can show that this guy is going to converge faster. But I'm not going to show you the proof, I just wanted to give you the idea. Do you see what I'm doing here? So you got the idea? Everybody's happy? Yes. Great. Okay, thanks a lot. So then you're going to do it like this. So this was the idea by Nesterov, and his idea was that instead of putting g itself, maybe I can go to the middle point. So this is some sort of approximation for the next point, and I can do it because I already have this guy. And I'm sorry, I think I have dropped this eta here. Sorry for that, eta should be here. But he did it like this, and then when you do with this, you compute this middle point, then you are going to compute your gradient at point w hat, and then you update your momentum with this g hat. You do not update your momentum with g itself. Everybody's clear? Any questions? Great. So if you look at the original paper or many textbook, you're going to see that the expression they show you for Nesterov is a bit more complicated, but that is exactly the same thing. The only thing is that they're combining all of these lines into one line. And then it's going to look a bit more complicated, but it's exactly the same thing. Any questions? Yep.
The calculation of the W hat, can you repeat it? Why this calling?
Why W hat is a better choice?
Yeah.
Because you do know that when you want to compute your WT plus 1, what you're going to do? You're going to first go from your WT to beta times MT plus MT minus 1, and then you move with your gradient, right?
Yeah.
So the question that Nesterov asked was that, why should I compute gradient at the point WT when I already know that I'm not going exactly with the gradient itself, but I'm going to move with the gradient plus the momentum, the previous momentum. So maybe I can just move with the previous momentum, I get into the middle point, and then I can compute the gradient. So the proof is a bit more tricky. I mean, if you want to show that this is going to converge faster than the normal one. But you can show it. But the intuition behind the idea is this one. Did it answer the question?
I will have a little bit think about it.
Okay, yeah, sure. So, now, what you have in PyTorch as SGD, this is actually including all the momentum and Nesterov momentum as well. So you basically have by default the momentum. The momentum factor beta is set to be 0, but when you set it something non-zero, then it's going to compute you the momentum. And if you set the Nesterov momentum to be true, to be valid, then it's going to just compute the Nesterov momentum. So next time when you use it in PyTorch, you already know what does it mean with the momentum factor beta, and what does it mean by the Nesterov momentum. Okay? And the choice of beta is usually very large, very close to 1. So 0.9 is a classical choice. And the main reason is that as the time passes, what you have is more reliable as compared to the new samples. So you're going to give more weights into that, less weights to the new ones. Everybody's clear? Any questions?
Can you explain why it's 0.9 again?
Sorry?
Why is it
0.9 because beta is the one which you multiply with the previous momentum, right? And the momentum itself is a better estimator as the new sample, right? So you're going to weight it more as compared to the new sample. When you put it 0.9, that is 0.1. Everybody's clear? Any questions? No questions? Great. Okay, so let's go for the next algorithm, which is RPROP. And the idea of RPROP is a bit older than other ideas. This was actually in 1992. It was developed by Reed, Miller, and Brown. And you can check the paper. It's interesting to see the paper, how they came up with this idea. So what they do in RPROP, the idea of RPROP is that you do know, if you remember from assignment 1, the assignment 1, and also in the first chapter, we talked about this fact. When we have multiple dimensions, then it might be the case that the optimal learning rate in every dimension is different, right? So for one dimension, you have maybe a very large learning rate, optimal learning rate, but for another one, you have a smaller one, right? And then we said if we want to choose one learning rate for all the dimensions, we should go for the minimum one, right? Because if we don't go for the minimum one, then some of those dimensions are going to violate that condition for convergence. Do you remember that discussion? So, in general, it is a good idea that you have your learning rate specified for the dimension. But the issue is that when you do this, you essentially you are dealing with the scheduling of a huge number of learning rates, right? Because for every dimension, if your problem is like ResNet with 10 to power 7 different parameters, then you have essentially 10 to power 7 different learning rates, right? And then you cannot schedule all of them. So the idea here was that Reed, Miller, and Brown wanted to see whether they can do it in a sort of implicit way. So this was the idea they came up with. So to understand it, let's first just think of one dimension, okay? So now I'm talking about one dimension. I have one weight. I have one gradient, one entry. This is just a derivative. So if I want to do gradient descent, what do? I compute the gradient GT, right? As you see here, I compute the gradient, and then I multiply it with the learning rate, and I then subtract it from my weight. This is my new weight, correct? Correct or not correct? Correct, great. So the thing was that what is the most important thing in my gradient? It's direction, right? And if you are thinking of one dimension, what is the direction? What is it? Sorry? Forward or backward. How you can show it? +1, -1. And this is basically the sign of your gradient, right? So they said, maybe we can replace the gradient with its sign. Okay? Each time, we just, instead of using the gradient itself, we use its sign. Is it still going to work? The only thing that is now more crucial is that I need to schedule my learning rate more accurately because I am just shifting all the weights and magnitude of the gradient to the learning rate, right? So they came up with this idea and they said maybe we can come up with one specific scheduler which is looking into the previous learning rate, looks into the previous gradient, looks into the current gradient, and tries to compute one new learning rate for us. Now, what is this guy? This is what I'm going to show you, and you're going to see this is quite simple. But everybody got the idea what I'm doing here? So I'm not using the gradient itself. I am using the sign, which is essentially the direction. And now I am going to do this scheduling more accurately. Okay, so how do I do the scheduling? This is the scheduling. You are going to start with some mu plus, and this mu plus should be more than 1. Okay? And now, when you see that the sign of your gradient is not changing, for instance, your gradient was positive, now it's again positive. What does it mean? If my gradient is positive now, and it's again positive in the next iteration, where is the minimum? Forward, right? Should I go faster? Yes, I can go faster, right? So if the sign of the gradient is not changing, I could just go faster. So I get my previous learning rate, I multiply it by a factor more than 1. Correct? You got it? So sign is not changing. The minimum is the right direction. So I'm going to move faster. But I'm not going to exceed some maximum value. So I'm going to stop if I get into a maximum value. Everybody clear? Now, what if I go this direction, so the sign is positive, then I come here, I compute the gradient, now it's negative. What does it mean? I already passed the minimum, right? Should I go again fast? No, I should go slowly, right? So I'm going to choose 1 mu minus smaller than 1. And then I am going to just reduce the speed now. So I'm going to reduce the learning rate with this factor which is smaller than 1. And again, I'm going to keep it above some minimum threshold. Clear? So the idea is quite simple. You just keep on going as long as you see that minimum is forward. You keep going forward faster and faster. And the moment you see you have passed the minimum, then you just get back slower. Right? Everybody's clear? So, this is the idea, and this is only for one dimension, right? So you can see it in this diagram. Here the sign is positive, at the next point is again positive. So when at the next point is again positive, or sorry, negative, both of them have negative sign. This means that I should keep going forward, right? And then in the next iteration, I'm going to take a larger step, right? And again, I see the same sign, so I'm going to go even faster, and then I'm going to pass the minimum, right? Now I see the sign got changed, so I'm going to get back slower, hoping that I'm going to get back to the minimum point, right? Everybody's clear? So this was the idea, and we're doing it in only one dimension, but what if we have a very long vector? Basically, we can do it on every single entry. So you get your whole gradient. For every gradient, you compute the sign, you compare the sign with the previous one, and you do the update of your learning rate exactly with the way that you did in the previous slide. If you do that, then you are eventually updating the learning rate for every dimension individually, right? And at some point, those learning rates are getting totally different. And you are hitting the target that you want without doing a direct scheduling, right? So this is the whole idea. So you're going to start again with a bunch of mu pluses, mu minuses, eta max and eta mean, and then you compute your gradient, and then for every single entry inside your gradient, you are going to update the learning rate of that entry exactly like the way we did it in the other slide. And then instead of the gradient itself, you're going to use its sign. And it's going to be the RProp algorithm. Any question? Great. So you're going to just do one dimensional RProp on every single entry, and that's going to be your algorithm. So, any questions? Yeah, go ahead.
What if we say the minimum point is behind us?
Okay.
And we go back, and the learning rate is then decreased.
Okay.
And now it's still ahead of us.
Then again, you increase, right?
And we increase it.
Yes, and then you might pass it again, then you decrease.
Why don't we just decrease it gradually?
Why we should decrease it?
Once we pass it,
Yes?
I don't think we have to increase it again.
No, you should. I mean, you don't just think about that simple diagram. It might be that you have passed it a lot, right?
Oh, yeah.
And then you decrease it, you still need to go faster. So you cannot say it generally. And don't think of one dimension, you have multiple dimensions, right? So your answer, the way you think is correct, but you cannot really implement it. It's a very case-specific scenario. So you cannot come up with a general algorithm. So this is why you do it like this.
So it's actually a safe choice too.
Yeah, it's safe choice, right. And it might be that you pass it again, but again you're going to decrease it. So it wouldn't be a big problem. No worries. So now, the classical choices for your values, like you usually start with something like 10 to the power minus 2 as the learning rate for all the dimensions. And you can leave it to just get it scheduled by the RPROP algorithm. And the classical choices for increase is 1.2. The classical choice for decrease is 0.5. This is not like a concrete choice, but typically we start with those choices. And those minimum and maximum values, you can come up with some big numbers and small numbers, and they are not that crucial because at some point you're going to get regulated, so you never hit them when your algorithms start to converge. One thing that you might pay attention is that you don't want usually to get 1 over mu plus to be exactly mu minus. Because once you pass this and you want to get back, you don't want to exactly update with the same learning rate, right? So you don't do it. So you're usually going to make it smaller than that. But again, this is just a numerical thing. So if you don't do it, you're still going to converge with maybe a bit of more iterations. Okay, so again, this guy is available on PyTorch, so you can access it and you can tune all of these parameters, and this is going to work for you. This is going to do the job. Yes?
We compute a different learning rate for each dimension?
Yes, but you don't do it explicitly. You just set one initial learning rate, which is going to be the same for everybody at the beginning. But gradually, when it goes up, because some of them are going to change sign, some of them are not going to change sign. And the learning rate of every single dimension is going to change, right? So after a couple of iterations, everybody has its own learning rate. Yeah. So if you are interested, you can try it and then monitor the learning rates at some iteration. You see that they are totally different. Any questions? Great. So if you got no question, then let me just go for the next part. So the next thing is that one observation that people did when they started to work with RPROP was that when they do the full batch training, RPROP is working fine, but when they go for small mini batches, it starts to work not that fine. And then the question was that what is the reason for that? So there is a very good answer to that, and I just try to keep it in a very dummy example here so that you understand what is the reason when you use mini batches stochastic gradient descent or mini batches with RPROP, then you're going to see that RPROP is not working perfect. The reason is given in this example. So I assume that you have only one weight, so we have just one dimension, it's not a big thing. And now you're using RPROP and you are using mini batches. When you are using mini batches, the gradient that you are computing, say you have 4 different mini batches, the gradient that you are computing on every single mini batch is changing randomly, right? So say, for example, over your first mini batch, the gradient is 0.1, over the second one is 0.1, third one is again 0.1, but last one is minus 0.5, right? Now, before I go any further, what would be your full batch gradient in this case, if these are your mini batch gradients? What it would be? You can say it. Minus 0.2 divided by 4, exactly. Do you see it? This is your first mini batch. Say you had 100 samples. This is the gradient you computed over the first 25, second 25, third 25, last 25. If I want to compute it over all 100, what should I do? I just average them, right? So if you average them, this is going to be the gradient of your full batch. Everybody's clear? right? Now, if you use the gradient of your full batch, what is this? Say your gradient in the previous iteration was positive. If you do the gradient of the full batch, what does our prop tell you? Does the sign change? With full batch. The full batch is average of this guy, which is negative, right? So sign is changing in that case, right? But now, if I use these mini batches, does the sign change in the first iteration? No. What about the second? Third? What about the last one? Yes, right? So this is the point. So if you just use these guys, I mean, when you have such a behavior, the thing that you see is that these are very small values and they could be very much mistaken. So your true gradient might be negative, but you are simply getting positive value because you have noise, right? And then this noise could be very weird in multiple iterations. So what you do with your full batch gradient is that you're going forward, you see the sign changing, so you go backward now, and then you're going at lower pace, right? But now, what you are going here is going that you keep going fast for 3 times, right? You go faster, 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 and then the sign changes, you go slower back. So you could be very well far away from the optimum point, right? So this is the main reason that when you use very small mini batches, this approach is not going to work perfectly because it relies on the sign, and sign could be very sensitive to that noise, right? You got the idea? So, moral of the story, our prop on mini batches is not perfect. Our prop on full batch is a good thing. And then there was a question how we can resolve this issue, which I'm going to do it after 5 minutes break and giving you a bit of break from this voice. Okay? So 5 minutes. Okay, shall we go on? So, the idea to get rid of this issue with R prop is the one which we call it RMS prop, root mean square prop. This idea was somehow developed by Geoffrey Hinton. Everybody knows Geoffrey Hinton? Yeah. Everybody knows him, right? Those at the end, not answering. Yeah, so you must know him, right? He won the Nobel Prize last year, right? Okay, so Geoffrey Hinton, he used to teach deep learning for a quite long time, and in his lecture notes, he came up with one idea to resolve this issue. Actually, he did not think of this one to be so crucial or so fundamental to publish it, so essentially he did not end up publishing it. He just had it in his lecture notes. But people started to see that it's really working. So what was the idea he was doing? He was just looking at this fact that this R prop issue mainly comes from the fact that you have a lot of variation in your mini batches, and these variations could make a lot of trouble for you. So what he did instead, he said, like, maybe I can look at the R prop from different point of view. So what is the point of view he is having? So he would say, I can write R prop in this form, right? So the new weight is the previous weight minus learning rate times the sign of the gradient. And I just update that learning rate with this R prop approach, right? Is it correct? So I can simply write it down in this form. Everybody's clear? This is the same thing we did, right? In R prop. Now, we can write down sign in this form, right? This is also sign. If you have a number, you want to compute this sign, you can divide the number by its absolute value, right? That's the same thing. If it's positive, it's 1. If it's negative, it's minus 1, right? So basically, he said, okay, what R prop does is basically compute, instead of gradient, is just dividing it by its magnitude. And now what we have is that this magnitude, this amplitude of the gradients is very noisy. So do you have any solution for reducing this noise? If you have multiple samples and they are very noisy, do you have any solution to get rid of that noise? Average. And if you want to do it online, how do you do that? Moving average. Great. So he said, why we don't replace this the amplitude with the moving average of the amplitude? And this was the idea he came up with. Okay? So first of all, the learning rates here, you see that I am writing it down in form of a vector, because learning rate is now specific for every single dimension, right? So you don't get confused. This is just the vector that you just updated with R prop. Everybody's clear? Okay, so he came up with this idea. Maybe I can replace the moving average of that amplitude. And the better idea, instead of replacing the moving average of the amplitude, I'm going to replace the moving average of the squared value. And then at the very end, I'm going to just compute the squared root. Okay? So he computed this value v. Now v is the moving average of amplitude of g squared. And everything here is a vector. You see it? Right? So you get your whole gradient, you square every single entry, and then you compute the moving average of that guy. Clear? Everybody's cool? Okay, so you compute this one, again for some beta, and then at the very end, when you want to update, instead of updating with gt divided by its own amplitude, you just update it with gt divided by the square root of vt. Okay? So just to see that this is exactly the same thing as before, let beta to be 0. When beta is 0, your moving average is simply your gradient squared, right? if you replace that one into this term, you're going to get back to the same thing, right? So this guy is R prop when beta is 0. If beta is not 0, is a more robust version of R prop. And it's going to get rid of that issue you see with mini batches. Any question? Now, one thing here, as you can see, I have dropped that eta being vector anymore, right? So I write it down in this form, and this was the reason, because once they did this update, they see that if you just get rid of that increase decrease, it's still working fine. So they somehow concluded that, okay, maybe we don't need that anymore. So that was all helping when we were not doing this moving average here. But when we are doing the moving average is giving us enough robustness that we don't need essentially that update anymore. You can keep the update, it's going to make your algorithm better, but essentially you don't need it. So it's not going to give you a huge improvement now. Everybody's clear? Any question? No question? Great, so this is what we call it RMS prom. The RMS comes from the fact that we are computing root of the mean squared, mean of squares, and then this is some sort of conclusion. So what you can say RMS prom is basically a stochastic gradient descent that you had before, because if you look at it here, you have eta times your gradient. This is exactly the vanilla stochastic gradient descent, but you are doing some sort of scheduling here because you have this guy. And this scheduling is somehow inspired by R prop. Okay? So that's it. So you have RMS prop in PyTorch again pre-implemented, and the classical choices for beta is again something very large, usually more than 0.9. So it's good if you have a 0.99 or something like this, very close to 1. And it's going to work much more efficiently. Any questions? No question? Okay, so that's it. And most of you nowadays, when you just come up with some assignment, getting it online, people tell you, okay, just write down this model, train it using the Adam optimizer, right? So Adam is the most used version of the optimizers that we have. And this was proposed again within UofT by Jimmy Ba. So you might know him. And it was proposed in 2015. And the main idea was that you get RMS prop, you are doing this R prop inspired scheduling there, right? And instead of the gradient, you replace the momentum itself, the moving average of the gradient. And then you're going to end up with Adam. So basically Adam is RMS prop with moving average also on the gradient itself. Okay? So what is the key idea? The key idea is that just go for RMS prop, which is a good idea because it's just doing a very good scheduling of the learning rate. But to improve your estimator, also replace the gradient itself with the momentum. So this is what we have. So we compute the momentum for the gradients, for the updating weights, and also we compute the RMS prop or R prop inspired what we do in RMS prop normalization, which is equivalent to doing scheduling. So if I want to write down the algorithm, it's going to look like this. Now, instead of 1, we're going to have 2 moving averages, right? One of them is M. This is the moving average of the gradient. One of them is V, which is the moving average of the squared of the gradient, right? So you're going to just compute the moving average for some beta 1 on the gradient and for some beta 2 on the squared of the gradient. And each time that you want to update, you're going to replace the gradient with the momentum, and you normalize it by the square root of the moving average of that squares. Okay? So now what you are doing eta divided by this green term. This is your somehow scheduling, right? And this is, the idea is coming from R prop. And this MT is basically the momentum of your gradient, right? So you somehow marry the two ideas together, it's going to work better, right? Any questions? Everybody's clear? No questions? Great, so if you got no question, then attention that any pseudocode that I have given you here is trying to just give you the main idea. When it comes to implementation, there are some delicate numerical details that you might need to read them as well, okay? For instance, if you start the moving average, you cannot simply start with 0. Because if you start by 0, then in the very first iteration, you just divide everything with 0, which is going to shoot you somewhere which you can never get back out of it, right? So you would never do that. There are some delicate ideas. For instance, you add some extra terms to give numerical robustness to your algorithm. I'm not discussing them here, but you can easily follow them. The main idea, the main purpose here is that I give you the idea what are those terms inside your optimizer when you're using them in practice. So, any questions? Yeah.
The rooming square that we were talking about here, is it a scalar or a vector or a matrix?
Sorry?
The rooming square that we were talking about here, is it a vector or?
That V, this is a vector, right? So it's the moving average of every single entry of your gradient squared. So you have the whole vector, you square it, then you compute the moving average.
Element-wise or?
Element-wise, exactly. Element-wise. Exactly like what you do with your gradient. No, just with the squared. Yes? So, any questions? Now, Atom is again already implemented inside PyTorch, so is I think, as I said, this is the most used version. This is the thing that you usually use in practice. And typical choices for beta 1 and beta 2 is 0.9 and 0.99. Usually your variance, you need to do more larger factor for it because the variance is changing more. It's squared, right? So it's changing more. You just want to rely more on your moving average. Any questions? No questions. Okay, so one last thing. So if you go on PyTorch, you just write down torch.optim and then dot, then you press tab. You're going to see a very long list. Okay? So these are not the only optimizers in the market. You have lots of more, but they are the, say, most successful ones. Okay? When you have any optimizer, they are always in two classes. Everything we discuss here is in the first class, which we call them the first order optimizers. First order optimizers, some people would like to call them gradient-based optimizers. And what are gradient-based optimizers? They are the optimizers that only use gradient. So they are not using any higher order derivative. Okay? So in all of these algorithms we did up to now, in each iteration, you just need to have one sample gradient, right? So you just go forward, backward, you compute that gradient, and now you have one gradient. You can compute all of those moving averages, and you can update, right? So you only need the gradient. This is a gradient-based approach. Order 1, first order. But you could have second order approaches as well, meaning that not only you rely on the gradient, but also you rely on the Hessian matrix. Okay? So the second order gradients. In each iteration, you not only compute the gradient, but you also compute the second order gradient, which is Hessian matrix, and then you use that matrix in order to update your weight. So we did not discuss it in this lecture. Some of you might have heard of the Newton method when you want to do the update, especially in the numerical analysis courses in your undergrad. These second order approaches basically use Newton method, but sometimes they use some sort of quasi-Newton methods. But at the end of the day, you need Hessian. And Hessian is not something that you can compute easily. Because if you want to compute one gradient, you should go once forward, once backward, right? If you want to compute Hessian, then you should go as much as your dimension forward and backward, right? This is not feasible. You cannot do it. It's very complex. So we don't use it typically because this is very, very computationally expensive. But if we could do it, then we could have better conversions, much better conversions. But it is not worth it in practice because in practice the complexity is huge. So one iteration of this guy could cost you like thousands or maybe hundreds of thousands of iterations of a simple first order algorithm. Okay? So it is better in practice, but it's very huge in computation. So there are some algorithms that try to approximate the Hessian matrix. You can go on checking them if you are interested, but again, when it comes to deep learning, we usually don't use them. Because deep learning means huge models. And huge models, even if you want to do pseudo or quasi-Newton approaches, it's still very expensive. We don't do it. Any questions? No questions? Okay, so if you got no questions, now we get into the new part. Sorry, just a second. I'm going to shortly get into this hyperparameter tuning part because I don't want you to be behind the schedule so much, but I try to make it short so you get less annoyed with my voice. The next thing we want to talk about in this chapter is about hyperparameter tuning. And when we started with the whole thing, I told you that we always assume that the hyperparameters are already given to us, right? So we assume that there exists one genie, and this genie is just telling us, okay, put that much of layers, that width, and so on, and then go ahead, right? But that genie does not exist, of course, right? So what we want to do today, we want to get it out of the bottle. We want to know how we can do the hyperparameter tuning or how we can find out what is the right hyperparameter. So one thing that many people at some point, especially those who have no enough knowledge in deep learning, started to say was that, okay, if we are going deep, we are having a lot of parameters, and if we can do the computation, okay, maybe go ahead and do more and more hyperparameters. So do it deeper, larger, more complicated model. This is going to help you more because this is going to have higher capacity, right? So this was the initial idea, but this is not really a good idea. You might say that, okay, this is because it is computationally complex. I don't want to eat a cupcake with a cell, right? So I don't want to have a very big model for a simple problem. But this is not the only thing. The thing is that if you use a very large model, you could at the end of the day end up with what we call it overfitting. And overfitting in simple words means that your model is so complex that it is understanding more complicated things than what is really underneath the whole data. Okay? To understand this idea, let me just give you a very simple example, and then you get what is the idea of overfitting. So let's say that I have one machine, and this machine, what it does, if you put one number x into it, it's going to give you one number y. And somebody knows that this machine is a second order polynomial with these weights. Okay? Since we are going to use this polynomial a couple of times, I'm going to write it down here. So the polynomial of this machine is, I think, x squared, right? X squared plus 3x plus 3. This is my true label, y, okay? Or maybe I'll call it v now, because this is my true label. So this is the machine, but this machine is not known to me. This is what we do in machine learning. We try to understand what is inside this machine. So somebody tells me that, okay, you do know that, let me tell you that the input-output relation is polynomial, but I don't tell you what is this polynomial. So what I want you to go ahead and do something to find out, or at least approximately tell me what is this polynomial. Okay? So this is the problem that I want to do, and I want to use machine learning. If I want to use machine learning, what should I make first? There are 3 components, right? What is the first one? No. 3, data set, great. Yeah. What is the second one? Model. What is the last one? Loss and training, right? So I'm gonna need these 3 guys. I need a data set, a model, a loss, and then that's it, right? Then I can just solve this problem, right? How can I make the data set? Any suggestion? I can test the machine, right? How can I do that? Bunch of random numbers input, I see the outputs, right? So I'm going to give a bunch of inputs xb into this machine, and for each of them I see what is the output, right? So this is going to be the output that I get, but the output that I have is not exactly accurate. Because, for instance, I'm using some measuring device which contains some thermal noise, right? And then when I compute, for instance, if I put 1 here, I don't see exactly 7, but I see, for instance, 7.1, because there is a bit of noise here, right? So this is what it is. I can do nothing, right? At the end of the day, even the most accurate measuring device contains some noise, right? So at the end of the day, what I'm going to do, I'm going to collect these noisy samples and I try to use them. So what can I do, right? So this is my data set. It contains a bunch of random inputs I gave to this model and a bunch of noisy outputs I collected from this machine, right? Everybody's clear? So that is my data set. So let's go for the model. The guy told me this is a polynomial, right? What does it mean? It means that the input-output is of this form, correct? Right? But I don't know the order of the polynomial. He didn't tell me, right? So what I do, I'm going to leave it as a general parameter here, right? Now, this is my model. What are the weights in this model? What are the weights? W0, W1, W2 till WP, right? These are the weights. What is the hyperparameter? P, right? I have a hyperparameter P. I don't know what it is, but I want to find the right one, right? So let's see. I can write down this guy in this form, right? So I can put all the weights here, and I can put all the x's here, correct? Right? And this inner product is going to be exactly this y here. You agree? Yes or no? Yeah? Okay, great. So I can call this vector the vector of features that I have here, which is basically my x taken to different powers to be my vector of hidden variables, right? So I'm going to call it like this, and then I can write down this model as a simple neural network. How can I do it? I can say that, okay, I have my x as the input, then I have p different neurons, p plus 1 neurons. The first one going to take the input to power 0, the next one to power 1, till the last one, right? And then the output of this guy is going to be x to power 0, which is 1, x squared, and so on, right? Then I multiply them with weights, and then I sum them up, which is again a neuron with linear activation, right? And it's going to be my output. Correct? So it's a neural network. A very simple dummy neural network, but it's still a neural network, right? Now, P, the width of the hidden layer is my hyperparameter. W is my weight that I want to learn, right? So the model is set here, the hyperparameter is set here as well, and the last thing that I need to do is to come up with the loss function. What is your choice for the loss function? If I see the output of that model and I want to compare it with the output that I collected, what do? How do you compare them? MSE, yeah. This is a very good choice, right? Because this is a real number, so it's a kind of good choice. So this is a regression problem. A classical choice in the regression problem is to choose MSE, right? So I have the three components, and now I can just start with the training, right? So let's go ahead with the training, see what's going to happen. So what do? I have my whole data set. I'm going to split it, right? I'm going to split it to one part. That part is what I call it training set. I have another one which we used to call it test set, right? I'm going to train at this training set, and then I check it on the test set, right? So now I do gradient descent to do the training there, and then when it got trained, then I test it on the test set. And what I'm going to do, I'm going to just plot the test set and also the test loss and also the training loss, both of them in one figure. And I want to see what's going to happen. So now what I am interested right now on is to see if I test this model and I change the value of P from say 1 and I go up, okay, to some large value. What's going to happen to the test loss that I get at the very end? Okay, so this is what I'm going to do. So I want to know if I increase the value of P, what is going to happen to the test risk. And if we want to go with the naive interpretation, this would tell us if I increase P, I should always get better, right? This is the naive conclusion. Larger model is going to give me better result, right? But do you agree on that? Do you think this is going to happen? No, it's not going to happen. So if you try that, you're going to see this figure. All right? So if you start with 0, meaning that you approximate the whole polynomial only with a constant, then it's going to be very high. Then you just increase P, it's going to be 1, and then you are just approximating everything with a line, then it's going to be still high. If you make it 2, which is the true value, you're getting a very small test loss, but as you increase it, you're going to get more and more loss in the next values. So, what is the reason here? What do you think? Yes, the model is trying to learn the noise, exactly. So this is one point of view that you could have. This is completely true. So let's look at it together. So what you concluded is totally right. So as we pass P equal by 2, the thing that is happening is what we call it overfitting. So overfitting simply means that since our samples are noisy, now our higher dimensional model or higher order polynomial is thinking of those noises as being a part of higher order polynomial. And it tries to fit to that with higher order polynomial, which eventually works very fine on the training set. But when it comes to the test set, it's not working fine. Right? So this is the idea of overfitting. So the overfitting, in a very simple word, it happens when you train a model, very complicated, on a data set, and then you get very good training results. But when you test it, you're not seeing that good training result anymore. It's getting bad. This is when you say that my model has been fed too much to the data set that I had that is not anymore capable of generalizing, right? And I think I have given this term generalization a couple of times in this course, but this is a sort of more concrete form of definition. So generalization simply means that when I use my model on new data, I'm seeing the same good result that I was seeing when I was training the model. Meaning that new data is also getting very well matched to this model. So the model has not only been matched to the data set that I had, it's somehow fitting into the whole data space, meaning that it's generalizing beyond the data set I had. Everybody's clear? Any questions? So, if you want to think about this, so yeah, this is the moral of the story. So, trained model, when it generalizes, it does what it does, what it did on the training data set, on the new data as well. Now, if you want to think about the example we had, here in this example, these are the samples that we have collected, right? So the samples are coming from this original polynomial. So this polynomial, the blue polynomial that you see, is what we have it on the board, right? This is the polynomial. But in your data set, you don't have samples from this polynomial, right? You have a bit of noise. So instead of sampling here, you're sampling a bit below. Instead of sampling here, you're sampling a bit above, right? You get these guys. And now what you're going to do, you are just giving a very high order polynomial. And you want to fit it into this data set. What is going to happen? This polynomial is going to perfectly fit to the data, right? Because it has a high order. You can just pass a very high order polynomial from these sample points, right? But now, if you get any new point, if you want to think about the difference between the true model, the blue curve, and the gray curve, which is what you have learned, you can essentially have a very huge difference, right? You can essentially have huge difference. So look at these bottom parts, right? Whereas if you fix your model to be of a smaller dimension, meaning that you keep your hyperparameter to be exactly equal by 2, then you are getting some model which is not perfectly fitting your data set that you have, but when you have new data, it's better approximating the true function. Right? Everybody's clear? So this is the idea of overfitting, and we always want to have the hyperparameter such that it's not happening. Because if it's happening, then it simply means that we are just trying so hard in training, and we do a perfect training, we fit it perfectly to the data set, but that model worth nothing. All right? Because you just give it to the new data, it gives you totally nonsense. Clear? Any questions? No question? Okay, great. So, there is one other side to this story, and that is when we have underfitting. Underfitting simply means that when we put our hyperparameter below what it should be, for instance, in this example, when instead of p being 2 or more, we are just setting it to p equal by 1 or 0, right? Then this model is not capable of fitting to your training or generalizing beyond that, right? So this is what we call it underfitting. So underfitting happens when you have no fitting in on your training data set, and also you cannot generalize. This is something that you don't want as well. But usually in nowadays models, this is not going to happen because we are using deep neural networks which are very complicated models. They are usually capable of fitting to our data set and even overfitting to that. So going underfitting, that is quite naive nowadays. This is not really happening. And this is why you don't have this discussion too much in the literature. So you have approaches to avoid overfitting, but you don't really talk about underfitting. Okay? So in the example that we had, the underfitting simply means that, for instance, we set p equal to by 1. And if p is 1, then it's going to be a line, and then this line would never ever match the data points that we have, nor the true function that we have. Clear? Any questions? So you are happy with underfitting and overfitting? Great, thanks. So now let's go for the answer to one very interesting question. And that is that, okay, we had this nice example, but what is really causing overfitting to happen, right? So in our example, you saw it, I had a very high polynomial, right? And this very high polynomial was not capable of was capable of overfitting to my data, right? But is it the only reason? I remember one of your friends when I asked this question, said that my model is fitting the noise. And this is another perspective to the problem, right? So there are different perspectives to the reason that overfitting is happening. So one crucial question is that why overfitting is happening, and there are different points of view to that which we want to answer, right? So one thing that just stop for a second. One thing that I missed to explain is the idea of validation. So what I wanted to talk about was, I guess, the next slide, right? Right. So I wanted to talk about the next slide. So before that, one thing at the end. When you want to do hyperparameter tuning, when you want to choose your hyperparameter, you need to do something that we call it validation. Basically what you're going to do, you're going to do the training, you test it. Once you test it, you see whether it's doing fine still or not. If it's not doing fine still, you're going to see that overfitting is happening, right? So you're going to reduce your model, for instance, reduce your hyperparameter, and you try training again, and you try testing again. And if it's now fitting to your new data, to your test data set, then you're going to say, okay, it sounds to generalize, so I have validated this one. I'm going to take this hyperparameter. This idea, we call it validation. And validation, we usually do it on a separate data set. So if you have your whole data set, you're going to get your training data set split, and then you're going to have validation on which you try to tune your hyperparameter. And once you did that, you finally go for the last part, which is your test set. And on that one, you're going to do the final test to somehow give a final thumbs up, right? So you couldn't use your validation set for test set because it's, again, a bit of cheating because you're just validating on that one, but it could be still that when you get a totally new data, you're still not doing fine, okay? So this is the idea of validation. So you're going to do the validation for multiple choices of hyperparameters, and then you can do you're going to take the one which is giving you the minimal validation risk or the best generalization on your validation set. Okay? Question? So, yeah.
What's the actual split for validation?
Sorry.
Split.
The split, ratio. So it depends on the problem you have. If you have like 20% validation, 30% test, and the remaining going to be 60%, training is a good choice. But sometimes when you are very low in training, you're going to reduce those two things. So you're going to shrink it, and you are going to increase the training set. Because we're going to see making a very small training set also could harm you in the overfitting. So it's a kind of balance. It totally depends on the amount of data you have. But if you are very rich in data, then 60, 10, 30 is a good choice, or 70, 10, 70, 10, 50, 20, 30 is a perfect choice if you are very rich, but then you can just drop it. So 60, 20, 20, 70, 10, 20 are also some typical choices. You can do it as well. Yeah. So, any questions? No questions? Okay. So, now, here in our example that we did, so this is the idea of validation. So what we basically did, we got our validation set, and on our validation set, we just trained for p equal by 0, p equal by 1, p equal by 2, and so on. And we see that the best test result, best validation result is going to be at p equal by 2. So we're going to say our hyperparameter should be 2. Clear? Yeah.
Why don't we just simply use the test set for the hyperparameter?
Yeah, because in this example, you don't see it immediately. But it might be that your overfitting is coming from the fact that you have not enough data. We're going to talk about this. if you don't have enough data, which is most of the time the case, I mean, we're going to talk about this in this chapter. Your data space is always super huge, and you're always living in a super tiny sub-manifold of that. And because of this, you would never be able to claim that you have enough data, that you have sampled very well your data space. If this is the case, then you could see it significantly different after validation on your test data set. Because again, your model and your validation, your hyperparameter, is somehow fitting to your validation set. And on the new data, it's not again generalizing. So you don't want this happen. That last piece is to just give you this hint that, well, your validation was not successful. And then you might ask me, okay, how can I get rid of that one? This is what we are going to talk in the sequel. Okay? But you cannot always rely on that validation set. Yeah? So we're going to give it, I'm going to give you a concrete example. Even in the MNIST, that data set that you have, you can by no means say that this is enough data to represent your data. Enough data samples to represent the whole data. You cannot say it. You're going to see it. Okay? Any questions? Yeah.
In practice, you have a lot of hyperparameters.
Sure.
And,
It's not going to be feasible. So this is what we're going to talk next. Yeah. So you're going to do it for very, important ones, very, very obvious ones. But you cannot do it for every single of them. Yeah. So any other question? No question? Okay, great. So if you got no question, then this is what your friend already asked. So in practice, we're going to have a huge number of hyperparameters, and this doesn't sound very feasible. Then I do hyperparameter tuning for every single of them, right? If you have 10 different hyperparameters and you want to do tuning for them by checking only 10 values for every single of them, this means that you need to train your model for 100 times, right? So it's not a kind of feasible thing. So what you do in practice, you might do it for very general hyperparameters. Like for instance, you don't know if you should go for ResNet 15 or ResNet 18. ResNet 15 or ResNet 134. Yeah, maybe these are two completely different models, right? Maybe you try to validate on both of them and see which one is giving you a better result. You're going to stick to that one. But then you cannot do the hyperparameter tuning within that one anymore. And this is why we need to answer this question, that what are the other means that we can handle hyperparameter tuning? So there are a bunch of means that we can handle the overfitting. There are other means to handle the overfitting, and they are basically the regularization, dropout, which is a special form of regularization, and finally the data augmentation. Okay? These are the things that I'm going to discuss here. There are other means as well, less famous but still feasible. And each of them is looking at the issue of overfitting from a different point of view. Okay? So the next thing that we are going to talk about this in this lecture, in this course, is to just find out when does overfitting happen in a neural network. And you might right now tell me, okay, overfitting happens if my model is too complicated for the task that I'm doing. But this is not always the best point of view. This is correct. But maybe this is because you have not enough data. Because, or simple example I'm going to show you, if you just reach your data set with a huge number of samples, then even if you go for a very high polynomial, it's not going to overfit. Yeah? So maybe the reason is that you don't have enough data, right? So this is what we're going to take a look at in data augmentation. Or maybe the reason is that you're not giving the same priority to every single weight that you have in your model. For instance, in the polynomial model, a very high polynomial model is still a second order polynomial model if I put the weight of the higher orders to be 0, right? So if I make my model to have 0 or very close to 0 weights for a bunch of weights that I have inside my model, then this model is going to better fit my data, right? So if I can tell my polynomial that you need to have at least 3 zeros in your weights, then it would definitely fit into the quadratic polynomial, even if I put p equal by 5 or 6, right? So again, this is another point of view which we're going to do with it, regularization, okay? So I initially planned to end regularization. We don't have time. Obviously, you're suffering from this voice, so I'm going to do it a bit faster next time. But please just keep it in mind, so I just do a quick wrap-up next time, and then we can go on with that. I really am sorry for this voice today. I wanted to cancel the lecture, but I thought maybe a bit of it is better than just doing a very compact lecture in few next weeks, especially that you have the reading week coming. So sorry for that. And also, I don't know if I should upload the video. I really don't want it to be published anywhere. But anyways, I'm going to do it. So thanks. See you on next week.